In Chapter 6, we will begin to focus on the normal distribution. The normal distribution is one of the specific distributions within the continuous distributions. In this chapter, we will learn how to recognize the normal probability distribution and how to apply it appropriately. We will learn to recognize the standard normal probability distribution and its connection to the normal probability distribution. This chapter introduces us to the normal distribution, which is the most important of all of the distributions we will discuss in this course. The distribution of many continuous random variables fit or approximately fits the normal distribution. There are two parameters for the normal distribution, the mean and the standard deviation. The normal distribution has a bell shape for a curve. This blue curve of the normal distribution is given by f of x, where f of x is equal to this nasty formula here. Now, we are never going to use this formula in practice, but I do want you to see it. The formula for f of x is the fraction 1 over sigma times the square root of 2 pi. And that fraction is taken times e raised to the exponent of negative quantity x minus mu squared divided by 2 sigma squared. Now, we will end up using our calculator or tables for finding probabilities within the normal distribution, but we need to know a little bit more about the normal distribution before we can get there. There's an endless number of normal distributions because each distribution is dependent on the mean and the standard deviation. You will always be given the mean and the standard deviation in this class. The formula is messy, and we have no nice way of calculating the area underneath the curve without using calculus. We do have a few tools that will make things a bit easier. We're first going to look at the empirical rule, its advantages and disadvantages. Then we'll look at the distribution table, the advantages and disadvantages, and then we'll look at calculators and their advantages and disadvantages. So starting with the empirical rule. If a distribution is normal, the empirical rule says that about 68% of the values lie between -1 standard deviation and +1 standard deviations from the mean. About 95% of the values lie between -2 standard deviations and +2 standard deviations of the mean. And about 99.7% of the values lie between -3 and +3 standard deviations of the mean. This graph here represents that well for us. We see the mean is in the middle, and then we see that approximately 68% is between those two lines where we have -1 sigma and +1 sigma. Then going out the same distance again, so we're now at 2 sigma, 2 standard deviations out in each direction. We have 95% of our data, and then another standard deviation out in each direction, and we have 99.7% of the data. So using the empirical rule, the mean height of 15 to 18-year-old males from Chile from 2009 to 2010 was 170 centimeters with a standard deviation of 6.28 centimeters. Male heights are known to follow a normal distribution. Let x equal the height of a 15 to 18-year-old male from Chile in 2009 to 2010. What percentage of males are between 157.44 centimeters and 182.56 centimeters? Now, in order to use the empirical rule, each of these values needs to be 1, 2, or 3 standard deviations away from the mean, either above or below it. So let's find the z-score of these values to help us determine how many standard deviations away from the mean these values are. Finding the z-score of our smaller value, we take 157.44 minus the mean divided by the standard deviation, and we get -2. Finding the z-score of the other data value, we find that it is +2. So the empirical rule says that about 95% of the data will fall between -2 and 2 standard deviations of the mean. So that means about 95% of males are between 157.44 centimeters and 182.56 centimeters. Let's use the empirical rule a little bit more. The scores on college entrance exam have an approximate normal distribution with a mean of 52 points and a standard deviation of 11 points. About 99.7% of the scores are between what two scores? Well, that percentage we see in the empirical rule. The empirical rule states that 99.7% of the data will fall between -3 and +3 standard deviations of the mean. So what value has a z-score of -3? Well, take your mean of 52 minus 3 times your standard deviation, and we'll get 19. So 19 would have a z-score of -3. We do something similar to figure out what has a z-score of +3. The mean plus 3 times 11 gives us 85. So what that tells us is 99.7% of the scores will fall between 19 and 85. Now, while this has been really handy to use the empirical rule, there's quite a bit of limitations that we've had. The empirical rule only works if we're looking for values that lie 1, 2, or 3 standard deviations above or below the mean. Most of the time, we are not looking for values at just those z-scores, so we will need to use other tools occasionally. The next tool that we will use is a distribution table. Distribution tables have been created by mathematicians for people to reference and find probabilities. These tables are handy, but because there is an endless number of normal distributions, we would need an endless number of normal distribution tables. The solution is to standardize the normal distribution. So let's take a look at the standard normal distribution. We can easily standardize the normal distribution by using z-scores. The standard normal distribution has a mean of 0 and a standard deviation of 1. Z-scores are found by the same method we have learned previously, so z equals x minus mu divided by sigma. When finding probability from the table, we will always want to be looking for the probability that z is less than little z. When we have the probability that z is greater than little z, we will rewrite it as 1 minus the probability that z is less than little z. When we have the probability that a is less than z is less than b, we will rewrite it as the probability that z is less than b minus the probability that z is less than a. So our tables are always going to give us the shaded area that is shown below. So the area that is to the left of a given value. In order to use a distribution table for the standard normal distribution, we first need to change p of x is less than x into p of z is less than z. We do this by using z-scores. So we're changing our normal distribution into the standard normal distribution. Once we've done this, we're able to use our tables. If you look online, you'll see that I've posted links to all of the distribution tables that you need, and I also have some of them embedded within this video here. Let's take a look at an example using tables. The final exam scores in a statistics class were normally distributed with a mean of 63 and a standard deviation of 5. Find the probability of scoring more than a 70 on the final. So we're looking for the probability that x is greater than 70, which is equal to the probability that z is greater than 70 minus 63 divided by 5, the z-score of 70. So that z-score simplifies to 7 over 5, which is 1.4. So we're looking for the probability that z is greater than 1.4. But we have to have a less than. We need to be looking for to the left. So we're going to use our complement rule here, and we have that the probability z is greater than 1.4 is equal to 1 minus the probability z is less than 1.4. At this point, we need to grab our table. So this is negative z-scores given to us on this table here. Since we are looking for 1 minus the probability z is less than 1.4, we want the positive z-score table. This table here shows the negative z-scores, so while it's useful, it's not what we need this time. Here's the positive z-scores. So since we are looking for 1 minus the probability z is less than 1.4, we want the positive z-score table. To find the probability, we will first locate the z-value along the outside of the table. Z-values in the table have 2 decimal places. One is found along the left and one is found along the top of the table. So since we just have 1.4, that's the same as 1.40. So we want 1.4, and then the first column is 0.00. So we want this row and column. So that gives us the probability there for that z is less than 1.4 is 0.9192. So back to our example here. From the table, we have found the probability that z is less than 1.4 is 0.9192. Thus, the probability that z is greater than 1.4 is 1 minus 0.9192, which is equal to 0.0808. So looking at example 1, you want to find the probability that z is less than negative 0.22. So if you are using a table here, you would find that the probability is 0.413. For a standard normal distribution, find the probability that z is greater than 0.9. Using the table, the value 0.9 for z-value is associated with the probability 0.8159. But that's the probability of being less than 0.9. So we need 1 minus that, which gives us a probability of 0.184. For a standard normal distribution, find the probability that negative 0.05 is less than z is less than 2.95. For this, we need both the negative and the positive tables. Finding our values, we have 0.9984 minus 0.4801, which gives us the probability of being in between is 0.518. Now we are able to work backwards. So the final exam scores in a statistics class were normally distributed with a mean of 63 and a standard deviation of 5. We'll find the score that would put a student in the bottom 15% of the class. So we are looking at probability of x is less than little x equals 0.15. Well, first let's standardize it. Standardizing, we're going to have the probability that z is less than x minus mu over sigma, which equals 0.15. And since we have a less than in here, it makes our lives a little bit easier. Looking at our table, we need to find a probability inside the table that is as close as possible to 0.15. The closest one that we can find is 0.1492. Now that comes from negative 1.04. So filling things in, we see that the probability that z is less than negative 1.04 is approximately 0.15. So what x value does that give us? Well, we can set up an equation where we have negative 1.04 equals x minus mu divided by sigma. Solving for x with a little bit of algebra, we get that x equals 57.8. So a score of 57.8% or below on the final would put a student in the bottom 15% of the class. Looking at example 4, again assuming a standard normal distribution, you're looking for the probability that z is less than c, which equals 0.0367. You're supposed to find c. So looking at your table here, c would equal negative 1.79. In example 5, again, you're assuming a standard normal distribution. This time you're told the probability z is greater than c is equal to 0.1423, and you're supposed to find c. Now the reason that I found 0.5877 in the table instead of 0.1423 is because we see the greater than symbol. The greater than symbol means we're really looking for the complement. So the complement would have a probability to the left then of 1 minus 0.1423. So that equals the 0.8577. And that's coming from a z-score of 1.07. Now, what limitations does the table have? To use the distribution tables for the normal distribution, you have to standardize to the standard normal distribution. These tables will typically only give z values between negative 3 and 3, and are often only accurate to 2 decimal places. The probabilities given are accurate to 3 or 4 decimal places, and there are gaps between the probability values, which cause for rounding errors when we have to select the closest option. When a higher degree of accuracy is needed, we must turn to our third method of finding probabilities, which is our calculator. So how are we going to use our calculator for the normal distribution? Well, calculators can be very useful. Underneath the distribution menu, you will find 2 useful functions, normal CDF and inverse norm. So when entering normal CDF, you're going to need your lower bound, your upper bound, mu and sigma. And when doing inverse norm, you need the area to the left, mu and sigma. Now here's just a guide for how to type these in. So if you have the probability of x is less than x, you're doing normal CDF of negative infinity, comma x, comma mu, comma sigma. If you're doing probability x is greater than little x, you have normal CDF x, comma infinity, comma mu, comma sigma. And if you have the probability that x is between a and b, you have normal CDF a, comma b, comma mu, comma sigma. If you're given c and you are looking for x, the probability that x is less than little x equals c, x is equal to inverse norm, c, comma mu, comma sigma. If you have that you're looking for c and you have probability x is greater than little x equals c, then x is equal to inverse norm 1 minus c, comma mu, comma sigma. Now we can't type infinity on the calculator, so we will use 1EE99 or negative 1EE99. Make sure when you type the negative, you do use the negative symbol, not the minus symbol. And this EE can be found above the comma. So you'd hit second and then comma. Remember, comma is above the 7. So let's do an example using some calculators. The final exam scores in a statistics class were normally distributed with a mean of 63 and a standard deviation of 5. Find the probability of scoring more than a 70 on the final. So that's normal CDF, 70, comma, infinity, comma, 63, comma, 5, which equals approximately 0.0808. Notice that when we round, we get the same answer that we got earlier on when we did this problem using the tables. Let's again look at an example we did before. Find the score that would put a student in the bottom 15% of the class. So using your calculator, you would say that x equals inverse norm 0.15, comma 63, comma 5, which gives you 57.817831, which is approximately 57.8, which is what we calculated earlier using the tables. Example 6 says that a manufacturer knows that their items have a normally distributed length with a mean of 13.3 inches and a standard deviation of 3 inches. If one item is chosen at random, what is the probability that it is less than 13 inches long? So that's P of x is less than 13 equals normal CDF negative infinity, comma 13, comma 13.3, comma 3, which is approximately equal to 0.4602. A manufacturer knows that their items have a normally distributed lifespan with a mean of 6.8 years and a standard deviation of 1.5 years. If one item is chosen at random, what is the probability that it will last longer than 8 years? Probability that x is greater than 8 is equal to normal CDF 8, comma infinity, comma 6.8, comma 1.5, which is approximately equal to 0.2119. A particular fruit's weights are normally distributed with a mean of 583 grams and a standard deviation of 40 grams. If you pick one fruit at random, what is the probability that it will weigh between 635 grams and 696 grams? So the probability that we are between 635 and 696 is normal CDF 635, comma 696, comma 583, comma 40, which is approximately equal to 0.0944. A manufacturer knows their items have a normally distributed lifespan with a mean of 9.4 years and a standard deviation of 2.4 years. The 6% of items with the shortest lifespan will last less than how many years? So we have the probability x is less than c is equal to 0.06. So c equals inverse norm 0.06, comma 9.4, comma 2.4, which is approximately equal to 5.7. So the 6% of items with the shortest lifespan will last less than 5.7 years. A particular fruit's weights are normally distributed with a mean of 612 grams and a standard deviation of 12 grams. The heaviest 18% of fruits weigh more than how many grams? So it's the probability that x is greater than c, which is equal to 0.18. Find c. C is equal to inverse norm of 1 minus 0.18, comma 612, comma 12, which is approximately equal to 623. Now that we have used the calculator for quite a few examples, we want to talk about the limitations that come with using the calculator. While calculators are wonderful tools, they are only as useful as you make them. By relying solely on a calculator, you are not thinking as critically about the problem. This leads to missed errors caused by entering numbers incorrectly or by using the incorrect functions. It is best to make sure that you have a grasp on approximately what the answer should come out to be, so that you are able to catch the calculator errors that can happen so easily.